Welcome to another podcast episode of Starting Out with Quantum Computing. My name's Lloyd, and today we are talking about, can quantum computers revolutionise hospitals and medicine? So quantum computers, they offer exponential speed and processing power. And so if we leverage these capabilities, is it possible to integrate quantum computation into hospitals? One of the main benefits of using quantum computers over classical ones is simply because quantum computers are able to handle large amounts of data. And quantum computers can help to simulate incredibly complex systems whilst using less resources. This makes them more efficient and less costly than classical computers. So you might expect, therefore, that quantum computers would have a role to play in medical research and within hospitals. Perhaps they could simulate new drugs, help identify medical conditions at a faster rate, or much more, at least accelerate medical research. And indeed, there has been significant development towards this goal, but we're not quite at the useful stage yet where quantum computing can actually help. So within this week's podcast, we're going to talk about some novel approaches to unifying quantum computing in medicine. And we're also going to address some of the corresponding challenges and discuss which research groups and organizations are trying to overcome them. Let's begin. So classical computers struggle with medicine, and particularly they struggle with the ability to handle the large amounts of data associated with medicine and hospitals. So if we consider just medical research alone, and the clinical trials and the patient information, the sheer complexity and volume of this data becomes challenging for conventional classical computers to process in reasonable timeframes. And this limitation can cause unwanted effects, such as delays in results and diagnosis. Current medical imaging can often produce images that blur the fine details or take ages to refine. This can increase the waiting time for successful diagnosis or even cause misdiagnosis. Furthermore, even though vast amounts of genomic data, so that's data based on the genetics, the genomes of a person, is collected with current medical technologies, there's the lack of computational power that our current technologies have means it is hard to derive precise, meaningful, and personalized results. And so without having personalized medicine, it can drastically increase the time taken for a patient to receive correct treatment and to receive a remedy, a medicine that actually works. Most notably, classical computers really struggle with drug discovery. And the reason for this is because in order to discover new drugs, you have to be able to simulate how individual atoms would bond and react with other atoms. Classical computers, they struggle immensely in the face of complex and large-scale molecular interactions. Each additional atom that you add on adds an exponential growth to the amount of variables that must be controlled, that must be kept track of and simulated. So with all this being said, the field of medicine can no longer rely upon traditional methods if it wants to advance. So enter quantum computers. Why are they so good? Quantum computers fundamentally operate in a different way to classical computers. With a quantum computer, we don't have to perform sequential calculations on every single variable that we have to think about. Instead, we can make clever tricks. For example, using superposition and entanglement. These are the fundamental quantum mechanical properties that quantum computers have. We can create a quantum state that considers all possible variables within a calculation. Then our quantum algorithm should hopefully output the correct answer to a high degree of probability. And this is how quantum computation generally works. Quantum computers do not simply output all answers at the same time, which is a common misconception. This is because when we actually measure the result that outputs from a quantum computer, we can only get one answer out of the machine. Therefore, a quantum state that is, a superposition of all possible inputs, is operated upon and is involved in the calculation, and we use clever tricks within the algorithm to increase the chances of measuring the correct answer. So this is one trick in the book. Another is the inherent nature of qubits versus normal classical bits. So a normal bit can only represent one piece of information, and if you add another one, then you can represent two pieces of information. But with qubits, each qubit you add will double the amount of information you can represent. So this is crucial because it means we can gather a small amount of qubits and represent something that's large and complex. Unsurprisingly, therefore, quantum computers can be advantageous when it comes to simulating intricate real-world systems or for solving optimization problems. Since the quantum computer can explore a vast space of potential solutions in parallel, which beckons the term quantum parallelism, see our glossary to understand that, we can use quantum computation to speed up the time taken to get answers and results. A final thing to mention is, of course, cybersecurity. So even though the advent of Shor's algorithm essentially opened up Pandora's box, it also provided hope for digital encryption and safety. So researchers are currently developing quantum-resistant encryption methods and protocols. We call this field post-quantum cryptography. And equally, there's another closely associated field known as quantum cryptography, and that might also show benefit. By leveraging the innate quantum mechanical properties of qubits, we may be able to create completely secure channels of communication and secure sensitive data. The possibilities and novel applications that quantum computers offer seem promising and futuristic. So, what could quantum computers actually do in medicine? So, we just spoke about it just a second ago, quantum cryptography. So, hospitals and medical practices deal with and transfer large amounts of confidential data every single day. That can be within the hospital or that can be to other practices as well. And so quantum cryptography offers a way of encrypting this data, securing this data to ensure it doesn't fall into the wrong hands. The most notable form of quantum encryption is quantum key distribution, which was first developed by Charles Bennett and Guy Le Brassard in 1984. One of the first QKD, quantum key distribution protocols, known as BB84 protocol, relies upon encoding information into quantum states and sending them to another party. Generally, we use a property of light in this protocol known as polarization. And what is so amazing about this mechanism is that an eavesdropper can easily be detected simply when both parties compare their results. Therefore, quantum cryptography can secure sensitive patient data even when it is being transmitted between different healthcare organizations. A second benefit to using quantum computers in medicine would be drug discovery and research. In order to discover new drugs and new reactions, we must simulate the molecular interactions on a computer. And as we increase the number of molecules, so does the complexity of the whole reaction increase. Quantum computers, therefore, can help to majorly reduce the time required to process these simulations. For example, in July 2024, a team of researchers demonstrated and implemented a hybrid quantum classical approach in order to address covalent bond interactions and energy profiles. They showed that the current limitations of drug simulation could be overcome by quantum computers. If you're interested and want to read more about that, please check out my written article. As quantum computers offer increased capabilities, we can start to design more effective drugs and significantly reduce drug screening times, which in turn would reduce costs and speed up the time taken for helpful medicines to reach public markets. Another benefit to quantum computation in medicine is genomics and personalized medicine. So, if we can personalize medicine based on the genetic data of the patient, it would allow us to determine the most effective treatment. And although the data associated with the genetics is voluminous and complex, quantum computers are able to handle this with ease. There's serious potential here, and this can be seen by looking at who's funding who. So a research collaboration led by Dr. Stralchuk of Cambridge University has been awarded $3.5 million to explore the potential of quantum computing for improvements in human health. More specifically, the team will focus on pangenomics, which is the study of the union of all genetic material within a species. They hope to show that quantum computers can be fruitful in the analysis of DNA. And in the long term, being able to decipher complex genetic markers will enable clinicians to prescribe medicine that is more likely to work for the individual. Finally, let's talk about quantum medical imaging. So we can use quantum computers to enhance medical imaging. You might have been to hospital before for an MRI appointment or an X-ray. In the world of quantum, there is a promise for enhancing the precision and resolution of the resulting images from processes like this. Quantum enhanced MRI can generate better quality images to help doctors properly detect abnormalities much earlier on. Equally, quantum sensors are much more sensitive than classical ones, meaning it becomes easier to capture images of soft tissues or neural networks. Take, for example, a research group in July 2023 who managed to use a diamond quantum sensor to record the weak magnetic fields induced by the currents within the brain of a mouse. These advancements prove that we could lower the time taken to generate an accurate MRI scan, meaning the patient spends less time in strong, harmful magnetic fields. To read more about that research, please take a look at my article. If quantum computers are so great, then why aren't they actually in the hospital? And unfortunately, it all comes back to the same reasoning. Unfortunately, and generally in all quantum computing, we reach the same dead end. We can't scale quantum computers to useful sizes until we deal with the errors that currently affect them. Quantum computers can require very specific and difficult conditions that can be challenging to maintain. This can include ultra-low temperatures and noiseless environments. We cannot have the quantum computer being affected by the environment at all, as this completely destroys quantum computation. And this makes the current implementation of quantum computers in hospitals both resource-heavy and complicated. Until we can graduate from the current NISQ, so noisy intermediate scale quantum hardware, we will continue to be plagued by high error rates. There's also quite a lot of regulatory issues that hospitals face when implementing new quantum technology, but this isn't a law or ethics podcast. Regardless, I like to take the stance that we should remain optimistic. The field of quantum computing is growing at an accelerated rate, mainly because of huge funding initiatives. And the future of quantum computing in healthcare looks promising and in some ways has already begun. Any development that we make in each sector that involves quantum computing can be transferable to healthcare and medicine, meaning that it is only a matter of time until quantum computers power the medical technology of the future. Sit tight, as one day quantum computers will blast through previous hurdles in medicine and change our lives for the better. Thank you very much for listening to this week's Starting Out with Quantum Computing podcast, and I hope to see you next week. Until then, bye-bye.